This is the 10th video supplement for CIS 351, Grand Valley State University's course on computer organization and assembly language. This video discusses functional completeness. Imagine you're in a factory that produces circuits. And although this isn't realistic, for the sake of the story, let's pretend that you provide on-demand services, that customers can walk up with a truth table and ask you to build the circuit on the spot. We know from video 8 that there are 16 possible 2-input gates, and 6 of which are useful enough that they're given special names. Of these gates, which ones do you need to keep on hand to be sure that you can handle any order that comes in? It turns out that you only need and, or, and not gates. The others may be nice to have, but they aren't essential. In other words, you can implement any truth table using only and, or, and not gates. We formalize this idea by saying that the set and, or, and not is functionally complete. I've also heard the concept called logically complete. So my first question is, how would you prove that and, or, not is functionally complete? In some sense, we've already done that. Video 1 gives an algorithm for creating a circuit from a truth table. Remember, we started with the inputs, and then we added the not gates. And for each row of the truth table that's a 1, we put in an AND gate, and then we connect them all with an OR gate. This algorithm is an informal version of what mathematicians call a proof by construction. Now, informal is the operative word here. If you were to put a proof into a math textbook, you'd need a lot more details than I've given here or in any of the other videos. And I'll leave that formal proof for the mathematicians. For this class, the important thing is that you have a reasonably intuitive sense that any circuit can be built using only and, or, and not gates. So given that, my next question is and, or, not the only functionally complete set, or are there other combinations of gates with that same property? So if and, or, not is the only functionally complete set, why is that? And if it's not, what are some other functionally complete sets? Pause the video and think about that for a minute. So it turns out that there are several functionally complete sets, and the most popular of which, after and, or, not, is simply NAND. So that's right, you can implement any circuit using only NAND gates. Again, pause the video and try that. So how could you prove that NAND is functionally complete? The obvious choice is another proof by construction, an algorithm that would take a truth table and show you how to create a circuit using only NAND gates. But let's not reinvent the wheel. Rather than building this algorithm from scratch, let's leverage what we already have, the algorithm for building circuits using and, or, and not. We can begin with this algorithm, then convert each and, or, and not gate to a collection of NAND gates. The trick, of course, is to figure out how to build these gates using NAND gates only. So let's start with not. How can you use one or more NAND gates to implement not? Here's a hint. Look at the 2 rows in the truth table where both inputs are identical. Okay, the trick is to recognize that when both inputs are identical, the output is simply the opposite of the inputs. As a result, this behaves as a NOT gate. Now, how can you build an AND gate out of NAND gates? This one is more straightforward because AND is just the opposite of NAND. So we can use the previous trick to simply negate the output of a NAND gate. Building OR out of NAND is the trickiest of the 3. The common approach is to use something called De Morgan's Law, which tells you that A nor B is equivalent to or has the same truth table as not A and not B. See if you can figure it out. All right, here's what you do. Negate both sides of this equivalence. When you do that, you end up with the OR you're looking for on the left side because the 2 negations simply cancel out. The right side is now a NAND, not A, NAND, not B, which we can implement like this. The 2 gates on the left are our NAND-based NOT gates, and then we can just use that single NAND gate on the right to tie them together. So this little subcircuit in blue behaves as an OR gate. These three little subcircuits now let us argue that NAND is functionally complete using the following proof by construction. You start with an arbitrary truth table, and you build the circuit out of AND or and NOT that we've already seen. And then we replace all the NOT gates like this, and then we replace all the AND gates like this, and we replace the OR gate like this. We now have a complete set of rules for building a circuit using only NAND gates. Now, this may not be the most efficient way to build this circuit using NAND gates, but our point here is only to show that it can be done. All right, let's do another example. How would you prove that the set AND NOT is functionally complete? This may initially seem trivial, but try it anyway. This proof has a shortcut I want to make sure you see. All right, I asked you to do this proof because I wanted to make sure you didn't do it the hard way. In general, when you're asked to prove something, take advantage of everything you know. In this case, use the fact that NAND is functionally complete and just show how you can build NAND using AND and NOT. Now at this point, you can simply replace all the NAND gates from the previous proof with this AND NOT combination. Again, not necessarily the most efficient way to build the circuit, but our goal here is just to show that it can be done, not necessarily to do it efficiently. One last exercise. Pause the video and see if you can find other sets that are functionally complete. All right, let's wrap up with some tips for writing proofs of functional completeness. You'll likely be asked to do this on a quiz or an exam. Be sure to use both sentences and diagrams. Circuit diagrams are much easier to follow than the written descriptions of how those gates are combined. I can't tell you how many tests I've graded where students have spent paragraphs explaining this little subcircuit and how it works, when all they really needed was one or two sentences and the picture itself. At the same time, pictures don't speak for themselves. You do need a few sentences explaining how the diagrams prove what they claim they prove. If I ask you to prove that a set is functionally complete, you need more than just 2 or 3 diagrams. The other big thing to watch for, and double check and triple check, because I guarantee it will happen this semester too, don't do the proof backwards. So for example, now this may be a bad idea, but I'm going to show you a wrong example here. So notice the red letters in the red background. This is wrong. The wrong way to prove that NAND is functionally complete goes something like this. You say, well, AND or and NOT is functionally complete, and I can make NAND using AND or and NOT, therefore NAND is functionally complete. That's backwards. That's like 0 points on the exam, right? What you really need to make sure you say is that you can build AND or and NOT using NAND. If you're trying to prove that NAND is functionally complete, it's NAND that you need to be using to build other things, not the other way around. So again, when this comes up on a homework quiz, test, whatever it is, double check that, triple check that. Somebody will do it, and it's a terrible way to lose points. All right, let's summarize. A set of gates is functionally complete if you can implement any truth table using only the gates in that set. And then to prove that something's functionally complete, you effectively need to give an algorithm for implementing an arbitrary truth table using the given set. Of course, the conventional way to do this is to use the shortcut where you start with a known functionally complete set, typically AND or and NOT, and then you show how you can build the known functionally complete set from the set you're trying to prove. Your proof needs to have both diagrams and words. Pictures don't speak for themselves. They do need some amount of explanation, but don't think that you have to explain every last detail in words. A picture is really worth 1,000 words. And finally, as we just went through, don't do the proof backwards. It's an easier mistake than you might think to make, so make sure that's on your mental checklist as you finish up any tests or quizzes. Okay, so what do you need to be able to do based on this video? First, if I give you a set and say, is it functionally complete? You should be able to figure out whether it's functionally complete or not. But more likely, I'll give you a set and I'll ask you to prove that it's functionally complete. All right, I know we wandered into the math side a little more than you might have been expecting for what feels like a hardware or programming oriented CS course, so be sure to ask lots of questions.